Welcome everyone to another OCP Tap call. This is call number 146. It's my pleasure to welcome Daniel Ammann, a distinguished leader in global navigation and positioning industry, to today's OCP Tap call. Daniel is best known as the co-founder of u-blox when he led the company's GPS business from its inception in 1997 through 2019. Over more than 2 decades, he played a central role in advancing GNSS technology and was instrumental in driving real-time kinematic. So now we know what RTK actually means, positioning, into mass market application. Under his leadership, u-blox introduced the F9P, which became a benchmark product in the GNSS community and helped make centimeter level positioning broadly available. Beyond u-blox, Daniel co-founded Sapcorda, a pioneering RTK correction service provider, and in 2021 he launched Onocoy, a community-driven, decentralized reference station network built on Web 3 principles. Onocoy's mission is to democratize access to high-precision GNSS by enabling anyone to contribute, participate, and innovate regardless of hardware platform. In today's talk, Daniel will introduce Onocoy, discuss the importance of hardware-agnostic ecosystem, and examine how much an approach promotes innovation and scalability across the positioning landscape. He will also highlight machine learning techniques for fraud detection and outlines Oncoy's internal quality assurance procedure, which established new standards for data integrity and trust in decentralized networks. Please join me in welcoming Daniel Ammann he presents building trust and innovation in a hardware-agnostic GNSS ecosystem. Daniel?
Great. Hey, thanks for having me. It's a pleasure. Daniel Ammann calling in from Zurich, Switzerland. And I don't want to repeat what Udon mentioned 2 weeks ago on RTK in a decentralized manner, but I think I'm going to add some more angle or a different perspective on something which is similar at the core, but then different. Also in the preparation, the team asked me if I could share a little bit more on the Web3 side, because the previous presenter was a bit short on that side, so I have some more slides explaining how that part works. So I don't need to repeat much on the intro. As I said, Daniel from Zurich, been in the GPS industry since 1997, have founded a bunch of companies, and more recently, in the last 10 years, have focused on the high precision side of things. First, from the hardware, and under u-blox, I was leading the department which created the first mass market capable RTK receivers, which ship in the millions today. And also then already in the direction of correction services, you mentioned Sapcorda. Sapcorda was a first attempt in making a system that is industry-wide, something which is not a centralized player following purely his own strategy, but more in a distributed manner. It ultimately failed, but I think now with Onocoy, we have a different angle to it with the secret sauce of Web3. So I'm going to focus a little bit first on what we do at Onocoy, the tokenomics side, and then, as mentioned, talk about a bit the quality assurance procedures. And guys, if there's anything that is unclear, feel free to either chat, I have the chat window open, or just interrupt me as we go. It's only 20 slides, but still, I guess we need to watch time a little bit that I'm not overshooting. So let's go. So Onocoy is very strongly linked to the work I've done in the GPS industry as part of u-blox. I was working on the first GPS in mobile phones, which it was in 1999, which was way ahead of its time. This was not the Nokias of the time. This was some unknown company, but it already had a dot on a screen or dot on a map kind of application that we take for granted today. But almost 30 years ago, that company was was pioneering that, and we put the first GPS in it. Commercially, a disaster, but it was pioneering work. So we moved on, we IPO'd the company, as I mentioned, then more into the high precision and started Onocoy. At Onocoy, going to talk about that a little bit, but in essence, we are providing RTK data. RTK as such, and at the risk of repeating, but just in a nutshell, in an RTK network, you have stations on the ground every 20, every 50 kilometers, which measure satellite signals from GPS and all the other constellations. And from the delays that you measure in a static, in a fixed location, from the delays observed there, you can communicate those error values to a moving device, which then in turn can compensate for those errors and then enable what is called RTK, which is a process, essentially a search process, in order to fix the unknown ambiguities that you have between your receiver and the satellite, so that you know on this 19 centimeter wavelength where on the phase you're sitting on each of the satellites. That's in a nutshell how GPS works, how RTK works. That's nothing new. We have not invented it. This technique goes back 20, 30 years even, where it was first found that you actually can track indirectly the wave of this 1.5 gigahertz signal that is coming from the satellites, and even determine where on this sinus wave you're sitting, with the problem of not knowing how many integer cycles are between you and the satellite, which is that ambiguity search. So far, so good. An industry has developed around that, typically in a more high value, low volume domain. So think survey applications, highest precision machinery like heavy construction machinery that needs to steer their operations with centimeter or even millimeter accuracy. So an industry is there, and they developed correction services and provide the data available to anyone who wants to use that, typically in a annual subscription model, in parts also in monthly subscription models. So if you look at the landscape of where do we have service globally, and this is just systematic, this is not an actual depiction because it would be way more fragmented, but in general, you have a number of correction service providers in the US, in Europe, in China, in Australia, and in Japan. And this is where the big business is. This is where everybody operates their own private networks of reference stations. Whilst outside of that, it's rather spotty. It's not such that there is nothing, but in each country, there's a different quality of infrastructure, different densities, partially regional players, partially government agencies who operate such networks. And in many cases, it's not modernized enough. So this is essentially the problem. So an oversupply, if you want, in the more developed regions of the world, and then underdeveloped regions outside of that. More importantly, though, the existing players, they have a business model which works on a basis of per device, per time. So if you are a farmer, you have an auto-steering tractor, you need to buy at least 1 month of data, regardless of whether you actually use it or not. And this is, we believe, something which is hindering mass adoption. If we think about robotics on the ground, if we think about drones, if we think humanoids, anything in the domain of automation and autonomy, this needs a precise location in real time and in a business model where you cannot charge $1,000 per year per device. That just doesn't scale when you go into mass markets. And that's what we have set out to change, not by competing, but by cooperating with the industry. But I'll come to that in a moment. Now, already on the previous slide, I used the term DPIN. I didn't really explain that, so I'd like to briefly explain what is DPIN. DPIN is this type of crypto projects or in general projects which build out a large infrastructure without any centralized components. So typically, if you're, for example, a mobile network operator, you plan out your network, you orchestrate that, you invest into your network, and then you sell the data services on that network. So very centralized. So you have a high CapEx, you have high OpEx to build out the network first. You, as the operator, are a single point of failure for the user bases. And it's relatively slow because it's slow to roll out new tech. You need to upgrade your network in one go. And that makes it very slow, very expensive, whilst you could be operating such networks in a decentralized manner. You could crowdsource the operations, the maintenance, the install in the first place through a community. So you could motivate individuals and small organizations to do something for a bigger network in a concentrated, in an orchestrated way. So through a crowdsourcing, each and every individual participating covers his part of the CapEx, but also of the OpEx. And through the incentives that they get, they also keep it running. This allows for a much more cost-efficient rollout. First of all, you don't have a huge investment up front, but also the operation is significantly cheaper. You don't need service technicians which go out in the field and maintain the stations, install them in the first place, find suitable spots, and then maintain them. It's all individuals that can operate that. Now, this obviously doesn't work for every type of network, but for many networks, this works well, especially when there's sort of best effort kind of networks, so networks which can live with a high level of redundancy and not necessarily need highest availability on the individual node in the network. This redundancy also increases resilience, and the innovation pace is significantly faster in that you can roll out new stations as you go. So you don't need to have all new infrastructure rolled out and then switch the backend. You have a backend where stations can join and leave, and you can make upgrades by just changing the rules of the game by incentives. So this type of networks are called DPIN, decentralized physical infrastructure networks. There's a whole class of projects which does that. The most prominent one is the Helium project. Many of you probably know the Helium project. It started as a LoRaWAN distributed infrastructure. They pioneered this model. They built up to 2 million access points globally. So they wouldn't stop at country borders. They would just motivate people to install such access points and then have a massive network available. The problem with that approach in Helium was they didn't find a market. So they had a huge infrastructure, but nobody was actually using that network. So Helium has moved on. They're now providing mobile network operator services. It's an extension to existing networks, which is essentially also what we do in the GPS domain. But there's also several other examples of decentralized networks, weather monitoring, for example, air quality monitoring, Wi-Fi sharing, just to name a few of those networks that can be organized in a decentralized manner. So that's what we do at Onocoy. Essentially, we are operating a community-powered DPIN GNSS reference station network. And this network has like two parts. It has a supply side and a demand side. The supply side is individuals who install such a station on their rooftop. They run a wire, a coax cable into a box, which is something like, it looks like a Wi-Fi router, a small one. And that box in turn connects to our cloud infrastructure. And this device, the antenna with that box, receives the GPS signals, provides those measurements back to us. And we issue a cryptocurrency to those people contributing, those people who provide data into the network on a per day basis. We're measuring the quality, the availability, but also the proximity to other stations, because we don't want to have 100 stations at one spot and then a wide field around it, but we'd like to have a as homogeneously distributed network as possible. Hence, we are adjusting the rewards if there is overpopulation. On the demand side, so the data that we're selling, this is a traditional business, so people can buy the data with dollars. They buy data credits and can consume the service. I'll talk about that in a moment. What we're doing is we're receiving the data from the devices in the field, we validate the data, we quality assure the data, and then we distribute it through the internet, and we settle the whole economics on the blockchain. That's in a nutshell what we do. It's a three-sided market. Our job is to set up the economic system, the rules, what do we measure, how do we measure it, and issue the tokens to the people contributing, and at the same time market the service to the existing potential customers. In a bit more detail, individuals operate reference stations. By the way, I can show you such an antenna if you see the video. So this antenna is a typical antenna that people put on their rooftop. It needs to be sturdily mounted because any motion of the antenna will translate into an error on the devices in the field, whether this is a rover that needs to locate itself accurately, or even for a time-only solution, any motion, any movement of the antenna will translate directly into an error in the end application. So that antenna needs to mount it fixed. And then people provide us the data, those who install that, and they earn our token. And in turn, on the demand side, people need to purchase data credits and they consume data. And what we are doing is essentially qualify the data, measure it, and distribute it. Around it is a governance system. So the whole setup is governed by the holders of the tokens. So unlike a traditional company where you would have shareholders and they would vote, here in the Web3, in the blockchain philosophy, all the decisions, the key decisions on how does the system work, what are the parameters of the system, are taken by the holders of the tokens, so that we have a decentralized governance as well. A bit more details on the economic part. I'll get to the technical side in a moment, but just to finalize the economic side, people provide us data, we give them the Honor token. Those people who operate stations, they can go to an exchange and sell those tokens, and they get fiat currency or a stable coin or another cryptocurrency that is tradable. And that's essentially the view of the operators. Whilst we as the project, we are selling data credits to data users. So they need to buy that with dollars. They get data credits, and those data credits they can use in order to consume data. And this is a pure pay-per-use, which is also radically different to what most of the industry is doing. As I mentioned initially, industry typically asks for a week or a month or even a year of subscription. In our system, you can buy just 10 seconds of data for a fraction of a cent if you wanted to, if your application just needs that. We can only do that efficiently because it is on chain. So nobody's actually doing anything manual. This is fully automatic. This is fully settled on chain, microtransactions. So the transaction itself of burning those data credits, of selling the data credits in the first place, but also burning them later on when they're being used, doesn't cost any transaction cost or just a really small portion. We are on the Solana blockchain, and Solana is the blockchain with the lowest fee and the highest throughputs, which is also why we've chosen it. To finish off this picture, so we are receiving dollars from people consuming the streams. And with these dollars, once we have sufficient revenues, we go to the exchange and we buy back the tokens. So this produces an upward pressure on the token price, while the sellers of the operator of the stations, they produce a downward pressure on the token value. At the moment, as it's early days, and there's not much buyback, and there's a few people selling, although most people hold on because they understand that the Ono token will appreciate in value once the flywheel is in more motion. But if people sell, then this will push down the value of the token, whilst once we buy back with the revenues that we make, this will increase the value of the token. We, in turn, when we buy back those tokens, we burn a portion of them. The reason we do that is we can make a deflationary system. So we start with a fixed amount of tokens, and we cannot create new tokens. This is assured on the blockchain. And from that moment on, we can only burn tokens. So we can only make fewer and fewer tokens, which means the remaining tokens, those which are in circulation, they appreciate in value because the whole value that we capture is then divided by fewer tokens. And that's the core of the economy that we're building. I mentioned governance around it, also investors, they're purchasing tokens out of those pools. So to wrap up the more crypto side of things, you could say we could be doing that also without the crypto aspect. And yes, we could. But the first and main reason is we would have to have a huge CapEx, huge capital expenditures, and huge OpEx in order to set up such a network in the first place. Through such a system, as we do it in a decentralized way, everybody contributes a little bit in investing into the hardware, in installing the hardware, and in operating the hardware. So the investment costs are shared amongst a large community. But it also allows us to do those microtransactions. If we were to do this in a traditional way, the cost of sales would be too high to even sell 1 epoch or 10 seconds of data. It wouldn't be a viable business because it would just, the cost is too high. Further, we can build on top, so we can build a governance which is organized and orchestrated on-chain. We can align and steer the incentives so that people operating such stations do the things in the interest of the network, like, for example, not everybody at the same place, so we can set up rules. How do we measure proximity, and how do we give penalties if too many people are at the same spot? How do we distribute the rewards, and so on. So I'm pausing here for a sec to look at the chat. Yes, there is a question. How is this similar and different from GeoNet? Yes, I have a few slides on that later on. I'll address that question then. Are there any other burning questions? Anyone? All right, then I would suggest I could very briefly make a demo how our system looks, just live. I'm actually going to first switch to my browser, one sec. How do I do that? Can you see my browser screen?
Yes.
All right. So this is our system, how it looks when you enter it. So currently we have 5,500 stations online. This number goes up and down a little bit. And then we can zoom in into stations. So this heat map shows you where do we have stations available. So those 5,300, they are across the whole globe with quite a few in Europe, in the west and the east of the United States, but also Australia, for example, is pretty well covered, and several other regions of the planet. We now zoom in to, sorry, I'm going to my home place because I have an antenna just one floor above me on the terrace. So this would be my station. To pick the right one. It doesn't seem to be online, the one I wanted to show. Let's go to a different view. So I'm providing data into the Onocoy network, and I'm earning also some tokens through that. And then I get a view on my station. So this is now my private view on what's happening here. So I see my rewards that I'm getting. I see statistics on how have I been connected, a satellite sky view, where we see in which direction of the sky do I receive the signal clean, or where is the blockage? Here in my case, in the southeast, there's a high-rise building which covers the lower elevations satellites as they rise in that area. So I wouldn't receive that, which gives me a mild penalty in the way we issue the rewards. I can also see here the number of neighboring stations that do impact. Now in our region, it's quite dense, so it's already overpopulated. So the rewards are being toned down because there's just too many. And so people are sharing the rewards because we are not paying extra tokens on chain because there's too many. Then some statistics where I can look at things like code and carrier phase RMS. So this is the measurements on the quality of the individual signals that we receive. The sky visibility percentage, as I said, I have a mild penalty because of that building. I'm reaching 92, 93% of the theoretically visible satellites. Can also go here to a live view and see what satellites are currently received from all the constellations, from GPS, the Russian GLONASS, the European Galileo, the Chinese Beidou, and the Indian Navig system. Then further, if I were a consumer of the streams, I would have a different view where I would also see my usage of the data and how many tokens, how many data credits has this cost me. If I go back to the global view, here we can also, if people want to contribute data, they can look at something which we call the opportunity map, which is a measure of how much more redundancy are we seeking, respectively, where is it already overpopulated? And if I again zoom into Zurich, we see here this gray area. So there's plenty of stations. We don't need any more stations here. So if somebody would be installing a station here, then they wouldn't really earn any further rewards. Whilst if you would install a station outside of here, for example, in this white area, here you will get 86% of the rewards, and then you see how much would that be in the token units, and which stations in the vicinity have what level of impact on a station that were here. If I would move it somewhere else here, I would already have 100%. And although we do have stations in this area, we are striving for a threefold redundancy. So we are still encouraging further stations in those domains. That was a very quick view on our platform. If there's any questions while I switch my screen, then please shoot. All right, one sec. All right, so we should be back on the slides. Does that work?
Yes.
All right, good. So moving on. What is the main purpose of RTK data in the first place? So our view into the future is today the main use cases is in primarily construction, heavy machinery, critical infrastructure, also timing for critical infrastructure, and precision agriculture. But there's strong growth in anything robotic, whether it's on the ground or in the air. As I mentioned, also robotics on fields and farms, humanoids, anything that moves and needs to know its location with at least centimeter accuracy in real time. They need such a service, and GPS is the only solution which provides a global globally referenced latitude, longitude information. Any other system is always relative. Whether this is maps or vision or UWB, it's always relative to some reference point. Well, GPS is the only truly global system. So that's why we find GPS often in combination with other sensors, but there's always a GPS in it in some form when it's an outdoor application. Moving forward, a large market coming up, and its early days, is autonomous vehicles. Although there is Waymos and Super Cruise on Cadillac and such applications, the volumes are not really high. So until this finds mass market acceptance and regulatory acceptance, that's probably going to be 2032, 2035 until this becomes also interesting business-wise. That's why we as a business, as an organization, we rather focus at the moment on ground robotics and aerial robotics. Now, the nice thing about the RTK, or a decentralized network collecting GPS information, is you're not only using that data for high precision GPS. The data also includes other physical properties that you can use for other use cases. Now, the delays from GPS are coming from the ionosphere and from the troposphere. And if you have a highly dense reference network on the ground, you can also use that information to predict or to estimate a very high resolution image of those layers of the atmosphere, which in turn gives you a view on humidity in the lower levels of the atmosphere, of the total electron count in the ionosphere, but also on the ground, because such a highly dense network also measures where are those antennas installed and how are they moving. So it also allows you to see things like very slow moving effects like plate tectonics on a large scale, so effects of centimeters per year, but also highly dynamic effects like millimeter per second motion on the antenna in real time. This in turn is interesting for infrastructure integrity monitoring, for weather monitoring because of the humidity maps that you can build, for structural monitoring, for plate tectonics, towards earthquake detection. So we are not only building a reference network that is of great use for anything in automation and autonomy, but also highly important on the Earth observation side of things. But I see there is a question as to precision. All right. Maybe I'll address the first question on PPP-RTK and PPP-AR on the next slide. And on precision timing, I'll probably also kind of cover it on the next slide, which is actually one of the answers that was earlier. What is the difference to what you guys heard 2 weeks ago on GeoNet? So in a nutshell, we are positioning ourselves in the market such that the existing industry can build on top. So it's a strategic horizontal positioning in the value chain. So this diagram shows a bit the value chain. There's people, they produce hardware devices, they make boxes and connectivity and everything else around it, so reference stations. And then people install such a reference station. We are collecting the data from such reference stations, and then we sell it to an open market. So existing correction service providers, they can and they are sourcing from us in order to augment and extend their existing networks. So that's the horizontal positioning that we are not crossing. We are not even trying to compete with correction service providers. We are offering them an opportunity to also add in data from our network. We could choose differently. If we wanted to, technically would be doable that we compete with them. but we believe we'd rather want to be useful for an existing, well-established industry that has been around for 10, 15, 20 years instead of competing. That also saves us the time of having to build up sales channels into all the different verticals, of developing different business models in different verticals and so on. And there is an industry, so we want to serve. At the same time, on the hardware side, we are agnostic, and I'll come to that in a sec. We're agnostic when it comes to what hardware can you use in order to contribute to the data, to our network, which means even if you have an existing hardware that you already operate, you can provide the data into the network. And I think this is the main difference between an Onocoy project and GeoNet. As we position ourselves horizontally and only, in quotes, to the blockchain part, the incentive schemes, and the business development to sell into an existing industry, GeoNet does the opposite. GeoNet has a proprietary piece of hardware that you need to buy from them, okay, although it's a different brand, but it's essentially the same people. And that device you can only use with GeoNet, but also on the demand side, on the customer side, those people the GeoNet is competing with the existing correction service providers. So they're going head to head and compete in certain market verticals. They cannot serve every vertical because there's just too many of those, and it's also quite fragmented. So that's in essence, the difference, horizontal versus vertical positioning. And I'm not saying the one is better than the other. There's both ways how you can do it. Apple is a great example of a vertically integrated company doing everything from the chips all the way to the end product, whilst a Google, for example, is quite the opposite, or used to be quite the opposite, where they're doing one thing in a value chain, and they're partnering and participating both on the supply side and on the demand side. So I think this explains a little bit the question, or answers the question on what is the main difference between a GeoNet and ours. In consequence, we are hardware agnostic, which is a challenge in its own right, and I'll come to that in a bit. The question was already also PPP-RTK and PPP-AR, if this is considered to be a threat to the Onocoy business. No, we don't see it as such. There's even free services, and I'm mentioning them here, RTK2Go and HOS. Galileo HOS is a free service. They're often making compromises when it comes to the level of accuracy that you can reach or the time it takes to reach such accuracy. PPP-RTK and also PPP-AR have the advantage that the bandwidth that you need from the correction service into the rover is much smaller and suitable for broadcast, which, for example, allows you to distribute the data to the clients through an Inmarsat link. However, if you are not bandwidth limited, like if you are on a terrestrial communications network or even a wired connectivity, bandwidth is not the main concern. The bandwidth in an uncompressed format is about 1 kilobyte per second. And if this is not an issue, then there's actually no advantage in having a PPP-RTK. Our advantage there, it's a stronger compression scheme. It's like a lossy compression scheme, where at the cost of more conversion time and less accuracy, you can squeeze the correction data through a thinner channel. But Oleg, I'll answer your question later. Please remind me if I forget about the precision timing with the antenna delay. I'll come to that later. Because I should speed up a little bit. Now, this is some examples of people who have installed antennas in our network. On the very left, you see a professional installation, a dome antenna. This has underneath, it has a very sophisticated antenna with rings which suppress multipath. It has a cover which allows it that, for example, snow is not building on top. It's likely also a heated antenna element so both snow and also ice is not on it, and a sturdily mounted pole, which then goes into a solid foundation. In our network, we are measuring how solidly it is mounted. And if there, for example, would be swing in the wind or the antenna is being moved, we could detect that. Those examples here, this, for example, is a good one, a very short pole, rigidly mounted, whilst this one here is surely not a good example. I would expect if there's a little bit of stronger wind that our quality assurance measures will trigger, and we will see that this is moving, and in turn it will give some certain reduction in rewards to the person operating it. But we've seen everything from highly professional installs to even temporary installs here with a solar panel and a box and antenna on top, which people put out in the field, let it sit there, and if they want to move it to some different place, we detect it, and then they can start mining somewhere else. Just thought it's interesting to see some impressions from the antennas. So where are we today with the project? As you saw in the demo before, we have about 5,000 stations. At the moment, this is strongly growing, and we are now also focused growth in areas where we see demand. We have the product is available since quite a while. Typical customers are correction service providers, people who already have a service who want to expand that or lower their own cost. And we're making revenues. Year to date, it's somewhere north of $100,000 that we sold, and this is strongly growing. We have a strong community, self-help, also in the community side, Discord channels, Twitter activities. We've launched the token in July. The token has tanked a bit since then, but also because we have not fully started with the token buyback mechanisms. We've been financing the project so far mostly with non-dilutive grants. We've also raised limited amount of money from investors, and now that the token is listed, we are doing OTC deals, so over-the-counter deals for larger investors who like to participate in future growth of our network. So that was more an overview of what we do on the tokenomics and the market. I'd like to dive a little bit deeper into what does it mean to be hardware agnostic. So in our system, if you already have a high precision GPS receiver, you can connect it to us. All the receiver needs to do, it needs to talk the NTRIP protocol, which is a HTTP style handshake mechanism. And then there's a data exchange in the RTCM3 format, which is a binary format that is supported by almost any receiver usable for high precision, and it builds on top of TCP. People who operate such stations and already have such stations, they can do that. And there's through this hardware agnostic approach, we have the advantage that we can address quite a large number of potential providers of data. So existing networks from government agencies, from private correction service providers, individual operators of stations, but also people coming more from a Web3 side, from a DPIN side, who participate in many such projects and also put an additional antenna and an additional box on their rooftop because they already do 10 other such projects. So any hardware that can provide that data is welcome, but we need to treat the data that comes as untrusted. So we need to verify that the data as such, that the people are actually entitled to provide the data, that they have all legal rights to the data, which is hard, but we have means by knowing stations that are not allowed to be injected, that are not allowed to be used for commercial purposes. But also we need to address the risk that people could inject data which actually do not stem from a physical device in the field. But we chose to go the hardware agnostic route because the pros, in our opinion, outweigh the cons, because we have a much broader source of potential providers of data. You can reuse hardware. You don't need to do your own hardware. So we as a project don't need to worry about supply chain and logistics and all about new generations of hardware because there is a market out there. There's hardware manufacturers. There's plenty. In our case, six companies have built purpose-built hardware, which is not proprietary to our system, but which can be used in our system with price points that are acceptable. On the downside, we have a heterogeneous network. We need to make this more homogeneous, and we need to have a significant focus on quality assurance. Just checking. All right. So what are possible attack vectors? People have tried to inject the same stream twice, or individual different people get the same data and inject it twice. People could try to generate synthetic data, which does actually not stem from a physical device in the field. They could take data from a physical device and modify it or obfuscate it. Or there is even sophisticated attacks where on the level of an RF broadcast, a spoofing transmitter could distribute data such that people are receiving data that is of no use or is misleading. That's a coarse classification of attack vectors. Whilst on the detection side, there's many properties in the signals that we can use. I'm not going to read out all of them, but essentially fingerprinting, looking at signals and classifying them from typical data, then looking at all sorts of physical properties that are in the data stream, whether this is ionosphere, troposphere, RF interference, antenna effects, and so on. And also machine learning approaches, where we have actually started with that, where we have collected a large data set of labeled data that we know is either known real or known non-real, whether it's a purely synthetic or modified synthetic data, which we are now feeding into a machine learning application. The project just started, and it's actually a project that is funded by ESA. ESA is the European version of NASA over here, with most European states and Canada supporting it. And they're financing a project that will look into machine learning, AI for classifying data, because the topic of spoofed data is omnipresent. This is a known problem in GPS in general. And with the approach that we're taking, we believe we can also bring science in this direction forward. I have some examples from the different attack vectors or the different things we've seen in the field. Unfortunately, not yet on the machine learning results. In about a year, we are probably there. The project just started 2 months ago. So we're still in the level of designing the network that we're going to train, of labeling the data, of collecting the data. But we already have some first insights. So one example how you could do fingerprinting is data. If you look at the data coming from a satellite over time, and if you plot the data here, and we see here the pseudo-range residuals, so the remaining error on the pseudo-range, so on the distance to the satellite, since we know the location of the antenna precisely to almost millimeters, and we know the location of the satellite at that point in time, we can calculate a residual, and we can plot this over time. And in a real case, this looks quite noisy, whilst in a synthetic case, this looks quite artificial still. In that case, there's been some attempts to model some elevation dependency, but it still doesn't look noisy enough. We look at the phase, and here look at the resolution here is, this line is 5 centimeters. So here you have a code phase noise of around 0.5 to 10, or 0.5 to 1 centimeter. And if you look at see those patterns, you see some effects which are likely multipath effects. And such effects can be used in a fingerprinting method to identify, is it from a physical device or not? Is it synthetic or synthetically modified? It becomes also quite visible if you look at the chart where you plot elevation and C/NO. Also there, the signal level, carrier to noise ratio, shows different characteristics. It shows some oscillations around certain levels. Next point here, motion of the antenna. This is an example where our real-time monitoring has triggered. So we suddenly see speeds of more than 5 millimeters per second, epoch by epoch. That station was a station in Turkey, actually here in the area of Izmir, on the western coast of Turkey. We then went on and tried to figure out where does this come from. Turns out that exactly at this moment, there was an earthquake in Turkey. So that station has picked up an earthquake. And if we correlate the time when this earthquake took place and when we collected the data, that means at this point in time, the earthquake must have happened. Here we only sampled every 30 seconds. So we missed the beginning, but we are also detecting earthquakes. And finally, a real-world example of spoofing. This comes from Ukrainian-Russian border, where we also see real-world spoofing. I'm not going to read out all the details here, but this is actual pseudo-range carrier phase measurements as they evolve over time. Initially, all stations in that area are jammed, so they don't receive anything. And then suddenly, step by step, new signals come in, actually spoofed signals, which sends then the position calculation 15 kilometers off. And after about half an hour, that spoofing stops, and then the signal goes back to normal and signal levels are back to normal. That's real-world spoofing. And with that, I'm coming to an end, just checking briefly the questions that we had in the chat. Precise timing, is antenna delay accounted for? Yes, it is. If you're solving on the antenna, what is typically done in high precision, there's a number of effects, and you're compensating the antenna pattern, the antenna phase center offsets, but also the elevation dependent effects with an antex file, so a file that knows what delay at what elevation happens and how are the phase centers of the different frequencies offset. Also delays on the cables, on the different frequencies are compensated. Those things are typically done in the receiver, respectively in the post-processing application. Then there was a question, what are the reasons that stream suppliers do not sell Onocoy tokens to cover the costs? Well, the reason why people hold the token is because they believe in the same vision that we believe in, that we can make a significant business and a significant value appreciation on the token going forward. It's very early days. We start to have revenues. We start to have a supply side that becomes relevant. And anyone who purchases the token now or who holds the token now, they will see I cannot promise anything because it's not financial advice, but we all work against tokens. So we all believe in that direction, and we all believe that this token is going to appreciate in value because the way the system is designed is we cannot make profits as a project. So all we can do is we can buy back the token and burn. So all the revenues that we're making directly or indirectly are value appreciating on the token once the business flies. And that's the reason why people hold on to the token. Then finally, a question, do you see RTK being used by consumer devices, phones, wearables? Not to the level of centimeters, because in a mobile phone, the antenna is typically a piece of wire, and it has a hard time maintaining those phase measurements that we need in order to make high precision. You can compensate the accuracy in GPS in mobile phones down to tens of centimeters, but for real high precision, you need really good antennas, which means typically larger than the mobile phone itself. So yes, the antenna are the decisive factor. It's also the chips in the mobile phones are often made for power saving and not so much for highly accurate measurements of carrier phase. That you could change with better chips, but this in turn adds cost. So many attempts have been made. Google had made a long campaign in providing raw measurements, and significant results have come out of that, but it's not consistent that you could claim that it's RTK capable. All right. And with that, I believe I'm like 2 minutes early. So if there's any further questions or any final thoughts, pick my brain.
Yeah, let's open the floor for more questions. Please unmute if you want to ask a question. Oleg.
Yeah, I wanted other people to ask questions. Otherwise, it's only me all the time. But I'm interested because you're dealing with like large data, basically pipelines. So you have so much data coming from miners, and I read somewhere your goal is to have like 100,000 stations, which will be a huge amount of data. So you must be employing some like big data techniques, and I'm more interested like how do you like you must have like data warehouses somewhere, or is this all sorted in the cloud at like lower cost? Maybe talk about this one a little bit.
Yes. So most of the data is just passing through. So we decode all the data, we do the quality assurance, like speed detection and such things, but then it's not being stored. So it's just a transmission from inbound, decoded, encoded, outbound. And the data is relatively low bandwidth. It's about 1 to 2 kilobytes per second, but plenty of them. So we're designing the system with 100,000 inbound streams with millions of outbound streams. What we are using in the background is it's a Kubernetes setup built around a distributed MQTT cluster, which is highly efficient when you have an N2M switch matrix that you need. And the MQTT clustering with the publish subscribe method allows us to have a highly efficient approach to this. We do store data on selected stations, for example, for the longer term collection, if you need, for example, 24-hour processing to determine the precise location of the antennas. But it's doable. It's nothing fancy. It's operating in a Kubernetes, so we can host it in Google Cloud, in Azure, in any cloud service provider, and even cross data centers. So it's not that massive.
And probably the data, apart from some rare analytical investigations and whatnot, is pretty much useless after, I don't know, a minute. Or what is the usefulness of the data?
It's about 2 to 3 seconds. So if you have latency beyond that, the data is not of use anymore in a real-time mode. You can extrapolate and you can do all sorts of tricks, but it's a few seconds. Now, there is a use case where you can do post-processing. So you're collecting data in the field, just raw measurements. Then you get a data from that hour when you were out in the field and post-process the whole thing. That would be a smaller business opportunity, but we're not doing that. We only provide data in real time.
Thank you.
Any other questions? All right.
I was wondering what something like with let's say these the efforts that we have toward these local things like BPS, I think, and things like this, like so you know BPS, right? They use the broadcasting stations to do timing. It's like they're kind of like LoRaN systems. I'm
Okay.
wondering, would those like with the inclusion of those technologies also help with RTK, or the model is exclusive for GNSS?
I don't think it would help because what you're compensating with a network like ours or any RTK network, you're compensating errors that happen in the atmosphere.
Ah, I see. I see. That
On
makes
then terrestrial networks,
yeah.
it's probably more multipath related signals. I
Mhm,
would assume troposphere plays a certain role
mhm,
for highest precision time distribution.
mhm.
But I must say I'm not an expert on terrestrial
Yes, yes.
time
Makes sense.
distribution systems.
Makes sense. Also, another thing with regards to past data, do you think, let's say just for the sake of your data relates to like ionosphere and like the activities you have in ionosphere, would that perhaps be useful for weather prediction in Lorentz models? Like when you have more history, you can predict better future, something like that.
I, well, I'm an electrical engineer and not so much into the more atmospheric and physics side of things,
Okay.
but I would assume more data allows more sophisticated models, especially
Yeah.
with machine learning approaches. And
Yes.
if you imagine there's about 120 or so satellites, navigation satellites out there from the different constellations, and you have we're targeting it to have 100,000 stations on the ground.
Mhm.
So every second, you get 100 times 100,000 data points to solve
Amazing.
that tomography problem that you
Mhm.
have.
Exactly. Yeah.
So you can build a highly dense real-time network of all sorts of layers on the
Exactly.
atmosphere.
You can perhaps like model, I mean, near real time, of the whole
Yes,
thing. Yeah.
indeed,
Yeah.
indeed.
You can
So
look
you
for
have a you
tornadoes,
have
for everything,
you have a passive radar with
Exactly. It's a
with
SAR. Yeah.
yes, indeed, indeed, and you're using the GPS satellites like your source radar source,
I didn't think about that.
you're
It's
the
very
receiver.
interesting.
Yeah, yeah, and
You have it
that's
well synchronized. Yeah.
yes,
Wow.
sure, it's all there,
Wow. Wow.
and it's in a way a byproduct of what you do in order to make devices, rovers,
Wow.
more accurate on the ground.
Yes.
It's
It's
pretty exciting.
very exciting.
And I think for science, the existence of such highly dense networks is of high value. Also, plate
Yes.
tectonics. What
Exactly.
often is
Tectonic
done,
planes. Yeah. Like when you look at, let's say, for example, this disruption in, like, let's say, a region on all the nodes in one snapshot, that gives you like the movement. That's very true. Wow. So you don't have an IMU on these systems,
no,
right? Wouldn't
no.
wouldn't wouldn't an inclusion of an IMU make things even better? Because I mean, this was actually something when we were making the time card, I added an IMU, and that was just the ambition I had. I wanted, and I mean, I looked for all kinds of excuses. I was like, the atomic clock is sensitive on a certain axis for
Yeah,
on yeah, but then I added an IMU just. It was not that expensive. It was like a Bosch IMU fully integrated was like, I don't know, about $10. But I mean, I had Oleg
yeah.
that was hell for it. So
Well, in quantities, those I'm used, they would come to tens of cents, maybe sub
exactly.
$1. And indeed, it would be interesting. However, this would mean we'd have to have a proprietary system, both hardware-wise, but also network standard-wise. Because
Ah,
that protocol that I mentioned, the RTCM3, that's an industry-wide standard. It does foresee extensibility with proprietary messages, but we don't want to go into that. We rather want to build something where any device out there can participate. But the other answer to your question is why? Because we can already detect speeds of the antenna with millimeter per second resolution. We don't need much more. We can detect earthquakes. We can detect poles swinging in the wind. If
yeah.
you just vibrate it a little bit, we see that in the measurements already
I mean,
using standard methods.
perhaps you can go from pooling to, like, to event based if you have also something there. But I mean, that
Yes, that
makes
you
things
could
more
do.
complex. Yeah.
That you could do, but the cost is quite high. You have to have proprietary
I mean, it
hardware.
can be provisioned at least.
Yeah,
It can be
yeah.
placed in the systems, and then it can be thought of how you want to use it.
And other candidates would also be pressure sensors.
Oh yeah, totally,
That
totally.
would be of interest, and various others. So
Yeah.
at this point in time, we're trying to stay hardware
I
agnostic.
think with that with the IMU works actually very well because they call it 10 DOF when you have also
Yeah,
the yeah, that will make everything.
indeed.
It's I think again Bosch has a very nice suite of sensors now that they come together. Yeah, that's very
Absolutely.
interesting. I'll
Indeed.
definitely
And
reach
I
out to
see,
you
sure,
offline, see how we can
sure,
collaborate on that.
absolutely.
Yeah.
Yes, you have my um, the QR codes I posted, they lead to
Yes.
our product and so on. Feel free to reach out to me,
Yes. And I
Daniel.
will get your I will get your slides. I'll get your slides and add them also on with the recording on the wiki.
Yes, I'm
Yes.
posting my email address. I'm also in the Web3 space. Everybody's on Telegram, so I'm also on Telegram. Then my
Yeah, maybe you can give you a number so we can
here's my Telegram
Telegram.
handle.
Yes.
So yeah, reach out if you want to discuss deeper or have some ideas or just want to
Wonderful.
participate in one form or another. I see there was another question by Jafar.
Yeah, Jafar.
I suggest you ask this question in our next AMA. I believe you also attended our AMAs, our monthly Ask Me Anything sessions that we do with the community.
Mhm.
We ran out of time over here, and I think that question that you ask here is better suited in the AMA.
All right. Perfect. Okay. So thank you again for the wonderful, interactive, educational presentation, inspiring, adding as well, and
Thank you.
looking forward collaborating with you and see everyone in 2 weeks by presentation by Bob Noseworthy. All right.
Well,
Bye, everyone.
hi everyone. Have a good day.